Hello, everyone, and welcome to today's webinar, the latest in the CARMA webinar series, Work Zone Use Cases. My name is Kevin Vita, and I'll be helping with facilitating today's webinar. This webinar is sponsored by the Federal Highway Administration and hosted by the National Operations Center of Excellence, also known as NOCO. NOCO offers a variety of resources to support the transportation systems management and operations community. In the upper right side of your screen, you can see a box called Useful Links. You can browse through those links for TSMO-related news and resources. There are also previous webinar recordings related to this topic and other topics as well at that website. Now I'll cover a few logistical items for today's webinar. We are recording this webinar, and the recording, along with the presentation slides, will be available through the on-demand learning section of our website. All of the attendees are on listen-only mode by default, but we'd like you to stay engaged by using the question and discussion pod for comments and questions that you may have at any time during the webinar today. We encourage you to enter them in the pod at any time. The questions will be read out loud one at a time by the moderator, and our presenters will answer each question. So that's all I have, and with that, I'll hand it over to our moderator for today, Nicole Palladot, to start us off.
Thanks, Kevin. Good afternoon, everyone. My name is Nicole Palladot. I'm a communications specialist with Leidos, and I will be your moderator today. Thank you all for attending. We are happy to share some informative content with you and also hear your questions about CARMA for work zones. So our presenters for today are Pavle from the Federal Highway Administration, who is the technical manager of the CARMA program's reliability research track, where he focuses on CDA research related to traffic incident management. Sudhakar from Leidos, who is a project manager for the FHWA Saxton Transportation Operations Lab. He directs CARMA projects and other projects for connected and automated vehicles. And Michael, also from Leidos, who is a software engineer overseeing design and implementation of solutions enabling CARMA systems to share and interpret information about the world in which they operate. We have a quick disclaimer before we get started. This presentation was created and co-presented by the FHWA and a contractor. The views and opinions expressed do not necessarily reflect those of FHWA or the US DOT. Our agenda for today is an overview of connected and automated vehicles, as well as the CARMA program and ecosystem. We'll then dive into the use case and testing for work zones. There will be a question and answer portion at the end of the presentation, but feel free to add any questions or comments, like Kevin said, into the chat pod as we go along, and we'll do our best to address all of those at the end during the Q&A portion. So first, we'd like to get an idea of who we have with us today. Please let us know in the chat pod where you all are coming to us from, your organization, your role, or just why you're interested in this topic. So let's take a minute to do that. Great, thanks everyone. Feel free to continue introducing yourselves in the chat as we go. With that, I will hand it over to Pavle to get us started.
Thanks for that, Nicole. Thank you everybody for joining us here today. As Nicole was saying, my name is Pavle Bujanovic. I am a technical manager here within the CARMA program. So briefly, I just want to give a quick rundown of CAVs, Connected and Automated Vehicles. I'm sure that most of you are very familiar with this diagram here that we have. It comes from the SAE J3016 standard. This has been around for a while, and As you can see, it starts over in level 0, goes all the way to 5, and kind of shows us the different levels of automation that we have. So I think most of you are familiar with this, but level 0 is obviously 100% human driven. And then we move on to level 1, where it becomes, starts to have some sort of automation, but it's just one component, either just lateral control or longitudinal control that you can get assistance with. Then in level 2 automation, we are actually able to combine these things. So this would be maybe like a Tesla has current level 2 automation where you're actually able to have longitudinal and lateral control at the same time. Then moving on to the green part of this diagram, this is where we actually have full automation. So in level 3, the car is fully driving itself, but you have to be able to take over at any time. That's why you have that little blue rectangle at one point in time under level 3, because you have to be ready to take control when the vehicle is not recognizing its domain. And then level 4 and level 5, that's when we're getting into actually having full-on driving automation, full-on automation that is level 4 being just at sometimes, and then level 5 is when you don't actually even need a steering wheel at all because the car is able to respond to every single situation. So as I said, this standard has been around for a while, and then last year, our office here at FHWA, we worked with a number of different industry partners as well as the SAE group, and SAE released the J3216 standard, which many of you may have seen already. As you can see, it keeps the levels of automation up at the top, level 0 through 5, but it now introduces the idea of classes of cooperation. And so I just want to briefly go through these. They kind of build on top of one another. So as you can see in the far left-hand column, we have Class A, and that's status sharing. So any of these levels of automation are able to engage in Class A status sharing type features. So what that means is they're able to send out the information about their status. So here I am and what I see. So, your basic DSM stuff, such as, your speed, acceleration, your current location, but also what you see. So what is the sort of things that your sensors are seeing so that you can communicate that out to others for the sake of helping them be more aware of their surroundings. Then moving on to Class B, this is intent sharing. So not only your current status, but also what are you going to be doing in the next 5, 10, 15, 20 seconds or however long in order to help us understand, okay, is there any potential conflicts that we need to be able to plan for? So if I send my trajectory plan to other vehicles around me, another vehicle might see it and say, oh, well, it looks like we might have a conflict if we keep on going on our planned trajectories. So that vehicle might make a change to his own path. Then moving on to Class C, that's where we actually build on top of this intent sharing, and we are actually doing agreement seeking. So, for example, if I'm trying to merge onto a highway in a congested area, I might ask somebody around me if they can maybe slow down or change lanes to allow me to have space to merge on into the highway. And then lastly, we have Class D, that's prescriptive. That's where we actually are going to do exactly as we're told. So, for example, in the case of platooning, if we choose to join a platoon, then once we're a part of that platoon, we can't just go rogue and do our own thing, as we agreed that we're going to abide by the rules of that platoon. So with that, this is where the CARMA program comes in. And so the CARMA program, what we're trying to do is actually do this cooperative driving automation research. We're trying to develop tools in order to support such research. So with that, the Federal Highway Administration developed this initiative, the CARMA program, in order to create a myriad of various tools that allow us to do this research. And the best part about it, in my opinion, is the fact that it's all open source, because we realize that there's so many different questions about this new topic and so many different unknowns about this new topic of cooperative driving automation that we really, as Federal Highway or no entity, can answer every single question on their own. And so what we're trying to do is create all these different tools that you can go and download from GitHub and install in your own systems, whether on a vehicle or an infrastructure, and you can test with us. You can test on your own. You can further improve the tools that we have and submit it back to us so that we can actually take it into account and then make it available for everybody else. And so again, what we're trying to do is we're trying to allow the community of research to leverage each other's research and basically get the most bang for the buck out of everybody's research dollars. So with that, I think Sudhakar will tell us a little bit more about the different components that we have as part of the CARMA ecosystem.
Thank you, Pavle. All right, CARMA ecosystem was developed as a set of open source software products and support services to accelerate cooperative driving automation R&D and encourage industry adoption of CDA. So the ecosystem consists of a set of CARMA products, they're listed here, evaluation program and collaboration, engagement program. Under the products, we have CARMA Cloud, which is a cloud-based traffic management system, which enables the IOs and traffic operators to exchange information with the connected vehicles. A platform is a software component that's running on the vehicle. Again, enables communication with the infrastructure and ability to control the vehicle. CARMA Messenger is another software component that runs on vehicles that don't have automation capabilities. It basically enables vehicles that don't have automation capabilities to be able to communicate with the other vehicles and also the infrastructure. CARMA Streets is a edge-based, software component. It basically enables us to deploy strategies that can be deployed on the edge, like at the intersection or on the, closer to the vehicles on the highways, and enable basically communication with the vehicles and the other actors in the ecosystem. CARMA evaluation is a set of products and services. Again, the CARMA simulation it enables establishing, a program that we are developing for everything in the loop, also known as XIL capabilities, to support CDA evaluation in a simulated environment. By building these capabilities through collaboration with the other agencies that are working in this field, like the Department of Energy and the CARMA community, we are designing and building tools to advance the understanding of CDA impacts on the transportation systems. This enables, as I said, us to test these capabilities in a simulated environment, and we are developing a co-simulation platform based on Sumo, Carla, and using Mosaic as the simulation manager. CARMA Safety involves human factors testing, both in the field and through simulation, including driver in the loop simulation using a highway driving simulator. The testing program, we are, as part of our program, we are testing at various closed test beds across the country. And we have information about these test beds, and depending upon the use case capabilities, that we need to test, we are going to different test beds and testing, and the testing program enables us to manage the logistics of reserving the test bed, transferring the vehicles, and such. And we are able to share this information with our stakeholders as well, because we have a lot of information about the various test beds. CARMA Analytics is a cloud-based data management platform. These the CDA vehicles generate a lot of data. So we built a data lake that is currently deployed in AWS cloud to analyze this data and understand the research benefits, and also to use the data to build, the machine learning models and improve the TISMO strategies, that we could deploy. CARMA 110 enables us to develop, testing of the CARMA features on a low-cost scaled-down robotic platform. We are building vehicles based on the 110th, the F110th, platform, for the passenger vehicles, and which enables us basically to test the same open source CARMA platform software that we are testing on the full-scale vehicle on the scale, version, which enables a low-cost entry for testing because we don't need to the researchers don't need to buy full-scale vehicles. They could test the same functionality on a scaled vehicle, and also decreases the dependency on expensive test tracks, and gives them flexibility for testing anytime. CARMA Engagement is a program where we are collaborating with the growing community of CARMA users, that Pavle mentioned before. We're working with a lot of different stakeholders, both from the government, the industry, academia, and other, infrastructure owner and operators. So it enables us to provide the CARMA stakeholders with the knowledge and technical support on CARMA program. We are able to do that through the support services that we have, and we could answer questions or assist in things like software troubleshooting of the CARMA products, with the systems architecture. If you want to build using the CARMA products, we are also able to support you regarding the message sets we are developing. CDA is all about the message sets that needed to be developed in order for the vehicles to communicate with the infrastructure and with each other. We could also help with the vehicle itself, with the hardware that's on the vehicle, and the data storage requirements and such. So all of these details are available on our Confluence site. The links will be made available. You'll see those in the presentation later on. But I think you would also see it in the resources section of the NOCO website. The Confluence site includes the information about the technical documentation about the vehicle, the software, including the design and architecture and everything, and also has a training and presentation about how to use CARMA and also develop using CARMA. Right. So the CDA, the research that we are developing is, we categorized into 3 different tracks. The first one is traffic, where we categorized all of the use cases that traffic operators, deal with recurring traffic condition use cases such as congestion, transit events, and traffic signals, etc. Reliability deals with non-recurring events such as work zones, weather, incident management, and others. Freight is the third research track, which deals with movement of commercial vehicles and goods, and also the port dredge related use cases, that are related to moving the goods. We are working with a number of US DOT partners that are contributing to our program, including FHWA, FDA, FMCSA, and ITS JPO program, along with others. All right, so let's take a look at the CARMA products in a little bit more detail. So the first among the CARMA products is CARMA Cloud. As I said before, CARMA Cloud is a cloud-based traffic management system that could enable communication with the vehicles by actually executing the TISMO strategies, based on the ability for CARMA Cloud to monitor traffic and weather and events such as from using the data received from the vehicles or external data feeds like weather data exchange or work zone data exchange. It enables engagement between infrastructure and the vehicles by providing lane-level traffic rules that the vehicles should follow. The vehicles use this information to plan their trajectories and motion for while they are navigating the roadway, basically. So it starts with when a vehicle is engaged and it knows its destination. It requests CARMA Cloud to provide any traffic control rules that it should be following within a geofence, that covers its route. The CARMA Cloud responds with information such as speed, the speed that the vehicle should follow, what is the lane status, and other information, any other controlling information such as the gaps that the vehicle should be following or platoon sizes, etc. So in order to come up with this message set, that CARMA Cloud provides to the vehicles, we reviewed the information that is available right now in traditional traffic management systems, such as systems objects, different model layers that we follow, and the standards that are currently being used. So we came up with a new message called traffic control message that uses the information from all of these information. It uses the geophysical information from HD maps that also contains the roadway furniture, that is on the roadways, and this information is overlaid with traffic controls, like I said, such as the lane states and any restrictions that apply to the vehicle, such as speed limits or any other physical restrictions based on vehicle type, etc. So we are, CARMA Cloud is able to ingest data from other sources using the data standards that we are already using, like TMDD, and the WGDX standards. Right. CARMA Streets is an infrastructure, edge-based application that enables us, the infrastructure, to share information with the vehicles on the edge, by enabling the vehicles to get the information such as signal states or any perception information that the infrastructure can provide to the vehicles, such as pedestrian information. This is it also interfaces with CARMA Cloud and enables communication between CARMA Cloud and the vehicles, where we are using edge-based communications such as DSRC at this time, and the same can be said with CV2X. It also enables provides the capability to deploy any services that could be run on the edge to improve the traffic, efficiency and operation. Okay, CARMA Platform, as I said before, is a vehicle-based platform that is built on top of ROS using a very modular, scalable design. The components in CARMA Platform can be easily swapped for experimentation with different combinations because we developed a plug-and-play kind of architecture. The same software platform works on both on the passenger vehicles and the trucks that are CARMA capable. It uses a set of software components called drivers, plugins, to sense the environment that the vehicle is in, to plan for it, and then control the vehicle motion. Drivers basically provide an interface to the sensors and the other hardware equipment that are in the vehicle by providing the data from the sensors. Planning plugins help with programming the vehicle behavior and trajectory, to exercise a particular use case strategy or cooperative interaction. Whereas controller plugin, allows the CARMA, platform to be able to program low-level vehicle motion planning, for acting. The CARMA platform runs on an industrial-grade GPU computer hosted on the vehicle, and it uses an IMU, to figure out the positioning and the motion. We have several, different, plugins that are already published on GitHub, and WorkZone use case that Mike is going to present next is going to we're going to demonstrate a set of features that go with that feature. CARMA Messenger is another CARMA product that is also vehicle-based for manually driven vehicle. It basically enables communication and cooperations with the automated vehicles, like other CARMA vehicles. The typical use case for this is a emergency vehicle or an inspection vehicle to be able to communicate with the CARMA vehicles to exchange information, such as in case of an emergency vehicle in traffic incident management. And emergency vehicles could transmit a geofence around it, and the rules that apply to the geofence, such as any lane closures next to it, or speed limits that the vehicles should be following within the geofence. So this use case basically demonstrates an in-field geofence that can be broadcast using using CARMA Messenger. Another use case for CARMA Messenger is for inspection. In case of CMVs, a highway inspector can send a message to the CARMA vehicle and download the inspection information without having to stop the vehicle. So the next product is CARMA Analytics. As I said before, it's a big data solution that is cloud-based, and we have a set of tools, that are deployed in the cloud that enable us to collect data from the vehicle and be able to analyze it, to understand, the data better and come up with strategies to improve cooperative driving automation. We deployed this in Amazon cloud at this time, but the same architecture can also be deployed on Google or Azure, other clouds, and this architecture and the scripts that we have developed, for this are available on GitHub. So we have, as I said already, these vehicles generate a lot of data. In the analytics implementation that we have right now, we've collected about 8 terabytes of data already, from the use cases that we have tested so far. So it enabled us to be able to analyze that data within the days after testing. So this has been a very helpful tool to understand the benefits of CDA. So for this, CARMA 3 was the initial program that enabled us to build the CARMA ecosystem, and the goal was to basically understand the emerging technologies and apply them to CDA and develop a platform that is SAE level 3 capable. We developed, we used a set of use cases, for this phase, we've basically developed scenarios for TIM, road weather, work zone, and basic travel use cases. We use those proof of concept to demonstrate, the capabilities of CDA and the ability to implement, TISMA and freight mobility strategies with them. So the goal was to advance this and also work with the community to increase the adoption of CDA and contribute to developing an open source CARMA platform. So the development of this ecosystem involved, various stages of testing. Starts with unit testing, where we test individual software components by themselves when we first develop, using what are called mock drivers. So these are independent, small software components that are, that we develop and test to make sure that they're working as designed, within the confines of that particular, component. Okay, so the second stage is integration testing, where we put different components together and make sure they are working together well, and to ensure that, the components can talk to each other and they're able to exchange, data and are able to work with each other using the interfaces, we develop those components on. Third is verification testing, where we test the whole system to ensure that what is built is built according to the system requirements, and we develop test cases to test end to end. So in this case, it could be, CARMA Cloud communicating with CARMA Streets, communicating with the vehicles, and also, the data that is collected being uploaded to CARMA Analytics and analyzing it, based on a set of performance metrics that we've come up with when we were developing the test cases. The fourth is the validation, which is an independent verification of the software and the capabilities that we have developed. This is to confirm that the system delivers, per the system requirements. And this, as I said, is done by an independent party. And fifth is a demonstration to basically show the internal and external stakeholders of the proof of concepts, that we have successfully implemented. Okay. With that, I would like to hand over to my colleague Mike Connor to walk us through the work zone use case and how we have implemented it.
Hey, Mike, are you muted?
Hang on, I think Mike may have dropped out. He's going to dial back in. Okay, let me take over. Kevin, can you confirm that you can hear me? Yeah. Okay.
We can hear you, Sudhakar.
Hey, so this is actually Mike. I'm in the same room as Sudhakar, and apparently my phone does not want to connect anymore. So you guys still able to hear me?
Yes, we can hear you.
Okay, thanks. So as Sudhakar mentioned, my name is Michael McConnell. I'm a software engineer with Leidos and the CARMA program, and I've been primarily working most recently on our work zone use case to do design and implementation. So let's talk about what that actually looks like. So when we're talking about a work zone use case, in this context, we're talking about basically a TSMO traffic management strategy for making sure that we can have work done on our roadways safely and efficiently by leveraging this automated and connected CDA technologies. So in this diagram you see on this slide, you can see that someone in the chat said it's a little quiet. Can you hear me any better?
We were able to hear you actually pretty well a moment ago.
Okay, I'll just keep going.
No, you were better before, much better. Yeah.
Can you hear me now?
Yeah, that's perfect.
Okay. Well, this is a great example of the world that we live in with remote video conferencing these days. So, as I was saying, the work zone use case is focused on basically transportation management, and we want to make sure that our workers on roadways can do so safely and efficiently. So In the current situation we have on our roadways, for the most part, workers come and they set up cones around the area that they're operating in, and any vehicle arriving in that area may be unaware that the work zone is there. It might have some information from, its GPS navigation service, but it's not going to know the exact geometries of the work zone it's encountering. So for an automated vehicle, that means it needs a fairly robust perception system in order to actually interpret the work zone that it's approaching and handle it correctly. Using the communications technologies that Sudhakar and Pavle were describing earlier, you can actually provide far more information to the vehicle by giving it the precise geometric positioning of the work zone itself, as well as access controls, as indicated here by the traffic lights. And this would allow our vehicles to basically approach the intersection precisely and in a controlled manner. So we have implemented a proof of concept of this use case using CARMA Platform and CARMA Cloud primarily. And we also used the V2X subsystem that Sudhakar had mentioned earlier for our RSU communications. So this demonstration involves an unobstructed lane change, a basically cooperative traffic monitoring and control by reducing the speed in the work zone through a speed advisory, a lane closure for the area of the work zone that's being worked on, and cooperative signal data in the form of SPAT messages communicating the signal phase and timing of the lights that control access to the work zone. So now I'm going to kind of walk through what that demonstration looks like. You might have a work zone set up with a traffic light on either side that's enabled with communications technologies. And you might have two cooperative vehicles approaching that work zone. The CARMA Cloud system provides the geometry of the work zone to those vehicles via the traffic control message that Sudhakar mentioned before. And it contains the lane closure geometry and the speed advisory for that area. Now, additionally, the traffic lights can communicate their signal phase and timing, so those vehicles can know precisely when the light is going to change and what its current phase state is, and respond appropriately. So the vehicle on the left can continue through the work zone, and the vehicle on the right can hold its position. This also helps reduce the need for a manual flagger to be positioned there. So it's more efficient and safer for all those involved. Once the vehicle has completed the traversal of the work zone, it lane changes back, and then the light will transition to green, and the other vehicle may proceed through the work zone area. Now, this whole process is basically handled in an automated fashion, and we've been testing this over the last few weeks. And we actually are wrapping that up at the moment and hope to have some results to share with you all in the coming months once we've processed all the data. So with that, I think I'm going to hand it back to Nicole.
Awesome. Thank you, team. Before we head into the Q&A portion, we'd like to remind everyone of the resources available for getting involved in CARMA and FHWA's CDA work. To join the community of users, reach out to karma@dot.gov or reach out to CARMA support@dot.gov for questions about implementing CARMA into your own research. To learn more about CARMA, also visit our FHWA GitHub, Confluence, and ROS Discourse pages. Now we will open the floor up for your questions, so please type your questions into the chat pod and we will start with addressing those for the whole group. Here's the slide with the links again, and this a recording of this webinar will also be posted after the webinar is complete, so these will be available to view there. First question, what's the CDA stand for? Cooperative Driving Automation.
Yeah, I typed it in the chat channel, but it stands for Cooperative Driving Automation, basically to enable the vehicles to communicate with each other through the class taxonomy that Pavle showed earlier.
Just to add to what the doctor said, if you search for the SAE J3216 standard that we discussed earlier, it's actually available right now for download for free. I think you just have to, create an account. So if you want to know more about CDA and exactly what the standard has to say about it, I encourage you to go ahead and download that. The reason I'm saying it's free is because usually these SAE standards are not free, but this one is.
Great, thanks, Pavle. We have another question. How would the vehicles being controlled, i.e. know when to stop and start, if there isn't a signal and you don't have the opportunity to apply SPAT, given that very few work zones actually use signals as presented in the use case?
Hey, Nicole, this is Michael. I'll give this a shot. So I guess there's two aspects to this. One is in a future world where this technology applies, we might have more prevalence of traffic lights at these work zones to enable the increased efficiency on the roadways. However, obviously in the interim, the questioner is entirely correct that many work zones do not have traffic lights. In that case, you would still need to rely on the vehicle sensors to detect the signage or the manual person flagging vehicles through the work zone. However, you still see a benefit from the more precise work zone geometry being communicated using the connection that you have with that data to allow the vehicle to have the most accurate representation of the environment that it's dealing with. So it does change the scenario a bit, but you can still see a benefit from this sort of setup.
Thanks, Mike. Our next question is, has there been any simulation testing with CARMA for work zone scenarios?
So no, for this particular use case, we haven't done any. We haven't tested it in the simulation environment, mainly because our co-simulation environment is currently under development and should be ready shortly. And we are planning on testing all of our future use cases in simulation first. Whereas for this, we tested it on the vehicles directly.
Great. Our next question is, are there more details regarding how CARMA will work with the work zone data exchange? Is there a cooperation between the two as they are both on GitHub?
So CARMA Cloud has an interface with the work zone data collection tool that was developed using the CARMA WZDX specification. So that is how we have currently integrated the work zone data exchange. So work zone data collection tool is another tool that was developed by USDOT under a different project, and it is open source too.
Great, thanks, Sudhakar. I'm just waiting. I think we might have a couple more questions coming, so I'm going to wait just a second before we wrap up. Is the work zone geometry similar to the map message?
So it is not like a map message, but as we've said, it's in the format that the automated vehicles understand. So that's the reason why we had to develop the traffic control message, which includes both the geophysical mapping of the work zone along with the other traffic parameters that are overlaid on top of it. So it's not similar to the map message.
Great. Well, I don't see any more questions. Oh, one more came in. CARMA's visual detection capabilities utilize the detection classification algorithm. Can work zone objects such as cones, barrels, and arrow boards be detected and classified with the CARMA platform?
Hello. So, yes, YOLO can be used with the camera data in CARMA platform to detect such objects. However, this platform itself is not going to do any kind of specific work zone detection and planning using those detections. Since this use case was primarily focused on the cooperative communications at the moment, but it's definitely an area of future work that could be pursued to improve the system.
Great. Okay, now I think we're really done. I don't see any more questions coming in. So thank you to all of our presenters, and thank you all for these really great detailed questions and for attending this webinar. I will hand it back to Kevin for some final comments.
Thank you, Nicole, and thanks to all of our presenters today, Pavel, Sudhakar, and Michael. We had some good information today. Thank you all for attending today's webinar. Like I mentioned and Nicole mentioned just now, recording of the webinar will be, and the presentation slides will be available on the NOCO website. On behalf of the National Operations Center of Excellence and our presenters, thank you for joining us today, and have a great rest of your day.